In this video, we're going to again try to imagine the shape of a surface of a graph based on its formula. What we note right out of the gate is that if our function is equal to y squared minus x squared, this is not the same sign for the x squared and the y squared, and so it's not an example with circular symmetry. So we have to resort to other methods. What we can do then is look at some other features. Where is our z value positive? Where is it negative? Where is it 0? Well, it's easiest to point out where values are equal to 0. Those occur when y squared minus x squared equals 0, or y squared equals x squared, or, well, that would be y equals x, y equals negative x if we take the square root of both sides. Now notice this is a question about domain, and so this would be drawn, being careful to label our axes at all times here, we'd be talking about a region of x and y, and then we'd be looking down, or thinking of this as a top view of the surface. So this is an alternative way to visualize a surface, and it's easier in the sense that we only have two variables to work. And this is easier in the sense that we only have two variables to worry about, the x and y, and then we imagine either being out towards you, above the surface, or down inside, below the page, as the z value coming out. What we just found was that when y equals x or y equals negative x, then we have the value 0. So along these straight lines here, draw this one a little bit more nicely, there we are, we have z equals 0. And it makes sense that if these are the values where we get 0 height, so this would be actually flat on the page, if we move out here and going to our increasing x, like we worked with increasing and decreasing functions, if we increase x, we're going to be subtracting more, and we're going to have negative z values. And in fact, that's going to apply even when x is, say, minus 5, it'll be squared. We're going to have negative z values here as well. So we're looking at the formula, we're looking at the barrier we found where the value of z was 0, and we can take it one step further and say if we go up into this region where we have larger y values, we're going to end up with positive z values over here, and the same thing in this region here. So if we're looking down from above, we see the surface coming up towards us here, and going away from us into the page in these two regions here. Now, especially if this is new to you, that might not be enough to really get the shape. So what we can try to do is build up the picture again by isolating a particular value of the variables and seeing what we get. So if we set x to a constant, what that's going to give us is a relationship between y and z. And the way we can visualize that or work with that is setting our x value equal to a constant, so it looks like a constant, like k. If we do that, then our z is going to equal y squared minus k squared. That's going to be our formula, but we can see this now as a constant. Well, if we have x equals 0, k equals 0, then we get z equals y squared minus 0. Oh, well, that's just a nice parabola. That's our classic, traditional, straight out of one variable calculus parabola shape. What happens as we increase our x, though? Let's say if we choose x equals 1, well, we're fixing our constant to be equal to 1 in our equation here and our formula. We're going to get z equals y squared minus 1, same parabola, but shifted down by 1. So what we're going to see is the second parabola if we have this with x equals plus 1. Just for comparison, if we have x equals negative 1, then what equation do we get? We're going to get z equals y squared minus minus 1 all squared. Hey, that's the same thing. We still get a parabola that's down by 1. Now, we definitely have a challenge here in communication, waving hands and trying to communicate via video here. But imagine that this YZ surface is your page. If we cut our surface right at the page, we get this parabola here. If we take a step towards you, out of the page, towards your eyes, then what we get is a cross-section that's a parabola that's moved down in the graph here. And the same thing if you move into the page. The out of and into the page correspond to x equals 1 and y equals 1. So we have a high parabola, and then we get a lower parabola going front or back. And you can imagine we're going to get further parabolas down as we move closer towards you out of the page or further away from you into the page. And that can be a bit of a challenge to visualize, so we're going to get there in stages. We're going to repeat our calculations here with our y values, and we're going to do the same thing. We're going to constrain ourselves to that being a constant. And so we would have z equals k squared minus x squared. And we know what these look like. These are parabolas, but because of the negative sign out front, they open downwards. And so if we're capturing the xz relationship, what we would see is a parabola opening downwards like so. That would correspond to y equals 0. And then if we do some other experiments, we would see that increasing y, which is this k value, is going to shift this graph up for us. That graph there would correspond to y equals 1, or, because of the squared term here, y equals negative 1. So again, this is a different view. This is like a left-hand side view on the surface. If we're right at the page and we sketch what the graph looks like, the surface, we'd see a downwards parabola. Then if we move out of the page a little bit, or into the page, y is now our third dimension, we're going to get the same parabola, except moved a bit higher. And you can imagine we're going to get other families of parabolas moving higher than that. As we make y bigger, we increase the intercept, we increase the vertical shift. All right, one last one. In fact, we've already done some of this, so it's a good practice just to remind ourselves of what we saw earlier. What we found was if we pick z equal to a constant, in particular if we pick z equals 0, that gave us a quite different relationship from the last two series. That gave us y squared equals x squared, or y equals x, or y equals negative x. And that was our straight line graphs like so. Those corresponded to height 0, and we had the negative z's here, and the positive z's and positive z's here. All right, let's try to put this all together. Going back, if we look at it, look at the surface in the y and z direction, we see upwards facing parabolas that start high in the middle and then go down as we move away. If we look in the xz direction, we see, in some sense, the opposite. We see parabolas opening downwards, but then as we move out of the page or into the page, those parabolas move upwards. And then we have this flat cross shape at height 0, and then regions where it's positive and negative. If we put all three of those together, this is the shape that we get. For those who have done anything with horses, this is typically called a saddle shape. If we label our axes, the y versus z we said was upwards bending parabolas, and as we take a step in the x direction, they go down, so that captures those parabolas. If we capture the x direction versus z, there we see the parabolas opening down, and as we move away from the axes, the parabolas still open down, but they're higher and higher, so we get that arch this way. And last but not least, when we look at our xy relationship with z and looking at the constant z values, you see that cross formation at z equals 0 that we talked about. And we also see the positive and negative regions. When we're in this region here, we have positive z values, as we do in the opposite side facing it. And then we have negative z values in the region between those two lines here, and also on the back side. That's a little harder to see in this particular diagram. So that was a whole pile of work to be able to think about the mathematical substitutions using one value, one variable, and treating it like a constant, and then being able to put that together into a visualization of the entire surface. Again, quite challenging, but it's important to be able to at least do the mathematical side of that and recognize what these cross sections here might look like. If you can connect these back to the full surface diagrams, that is when you've really put all the pieces together.